So we look at the stability problems with some example which we have considered earlier in the context of getting the Green's function. But we will look at from the point of view of our analysis. But before that, let me just recall. So we make a general statement about stability. Look at, this is our system. Now with the assumption that the determinant of this is not equal to 0, which assures that 0, 0 is an equilibrium point, is the only equilibrium point. Now from what we have analyzed, put them together, then you see that the eigenvalues indicate the nature of stability. You see that if we can say that the equilibrium is stable, if and only if the real part of lambda 1 and negative, or I would say non-positive. Because even when these real parts are 0, you get stability, you run into what is called the vortex points, which is stable. Yeah, but because we have seen the various cases that lambda 1, both lambda 1 and lambda 2 are negative, then we have seen that degenerate case where again the sign of lambda 1, or there is only one eigenvalue, the sign of lambda is negative, then it is stable. Then we have seen the vortex case where the real eigenvalue is the real part of eigenvalue is 0. There again you have stable equilibrium. And finally in the spiral case, alpha has to be negative. Okay. We can say that the equilibrium, the characteristics approach in cases where and in some cases they also enter, of course in the spiral cases none of the characteristics. Enter 0. You just don't know which direction in which they approach. They just go round and eventually collapse. That is the situation that you have. So there is no specific direction in which it enters. Okay. Whereas in all other cases, you see that when real lambda 1 is and real lambda 2 are both negative, in all situations they approach the equilibrium point, but in some cases they also enter. That we have already analyzed. So this is a part of the summary. Okay, now we look at an example which we have analyzed earlier. An example. It's a linear second order equation which describes one-dimensional motion of a particle. It's a homogeneous second order linear equation with k and q as constants, and we have the situation that q is not equal to 0, and let us first, so what we do is, this is a second order homogeneous equation. So we transform this into a system and then apply the theory that we have developed and read out the inferences from that. Okay. So we have seen this problem. What is this? This corresponds, suppose there is a unit mass particle moving, having a one-dimensional motion. Then you see that suppose xt is the position of the particle at time t, then the second derivative of x corresponds to what is called the acceleration, and if it is unit mass, then this term corresponds to what is called the rate of change of momentum. And then you apply the Newton's law, and you have got this rewritten in the form minus 2k this is the equation. Now suppose k is 0, then the equation is, we have seen the dynamics of the problem. See what this says, this is the rate of change of momentum. Rate of change of momentum is proportional to the impressed force, and we assume the constant of proportionality, etc. So there are two factors for the force. One that is proportional to x, so it is something of the form minus qx. If q is positive, then it is talking about a pull back to the center from the point where it has started, and once it crosses that, it comes back. So you see that if you have k equal to 0, then the equation is d2x by dt square is equal to plus qx equal to 0, and that leads to what is called the simple harmonic motion. It says the particle is moving like this. Starts from here, goes there. At some point it's what is called the momentum is 0, and then it becomes negative, so it starts moving in the opposite direction and then goes here. Just like a pendulum, it just moves up and down, oscillates. Okay. right? Suppose this is also there. This is what is called the damping force, which is, related to the velocity of the particle. Okay, so you see that if q is positive, then the velocity start decreasing. Therefore, suppose k is positive, then you see that you have a pull back to this direction, in the direction 0, and you see that the presence of what is called a damping force will make it oscillate like this. It will go here, come back, doesn't go to the complete extent because then it will be pulled back, then it will go like this, and eventually it will just collapse to the equilibrium point. This is the dynamics which I have explained while constructing the so-called Green's function associated with this problem. Now let us first convert this into a system. We denote by x dot. This is the classical notation of Leibniz. Sorry, I think Newton or Leibniz. I think Leibniz for derivative. Then you have dx dot by dt, that is this term. This is equal to minus 2k x dot minus 2x. So now you see, this is, you have two variables now, x and x dot. Now you see that the dynamical problem, suppose you know the position of a particle and the velocity with which it is moving, then you know completely what is happening to the particle. That is what you are, when you say that you understand the motion, provided you know where the particle is at a given time and with what velocity it is moving. So if you know x and x dot at a point, then you know the motion of the particle completely. Now this is the dynamical scenario. So by solving this system, this is the equivalent system. X dot corresponds to the velocity, x corresponds to the position. So this is what you have, xt okay. Now what is the system that you have for x dot? It is d by dt of zero 1 minus 2k minus q. In the physicist language, x dot is said to be a point in the phase plane. So this is a point So any point in the phase plane would give you the position as well as velocity of the particle. Okay, x corresponds to the position, x dot corresponds to what is called the velocity. So this is what is called the x dot plane, is what is called the phase plane. So let me denote this by 1, and that is essentially the same as this. Okay. Now here we observe that compared with our standard case, a equal to 0 and b equal to 1. That is, this is the standard case that we are looking at, where if you put a equal to 0 and b equal to 1, this is what you have: dx by dt equal to y and dy by dt equal to cx plus dy, where c is equal to minus 2k, d equal to minus q. That is the corresponding situation. Okay. So we make the following observations. Okay. First thing that you observe is this. You see, for any solution, we call this one, this has 2. 1, what do you get? You have x given, okay? And what is x dot? What is the relation between the two? You see that dx by dt equal to so what I want to say is not this, sorry. Okay, let us look at the eigenvalues of this. What are the eigenvalues of this? So the eigenvalues of this, what is the characteristic equation? Lambda square so we are actually, for eigenvalues, we go for the roots of this. Equation lambda square q equal to 0. Suppose lambda is an eigenvalue. With corresponding eigenvector x1 y1. Then what do you have? You have minus 2k zero zero. Look at the first equation. The first equation says that minus lambda 1 x1 plus y1 equal to 0. Okay. So from this what do you infer? You infer that y1 is equal to or lambda 1 gives the slope of the line x1 y1 of the eigenvector. Okay, right? This is a special case that we are considering where this here it is 0, here it is 1. Okay, so let me just note that. Assuming this lambda is real. Okay, so whenever lambda is real, from this you see that this is something like y is equal to mx, or you see that what is the characteristic corresponding to that? It's a rectilinear characteristic. The given by this is an observation that we make. It comes from this equation. Okay, now let us write down some inference. It's quite easy to infer the following. A characteristic crossing x dot axis can do so only in the negative direction. Why? Because you recall our earlier thing. So we had a, okay. So our equation, what is the equation that you have? Okay. This is the x-axis, this is the x dot axis. Okay. Now let us take a point here which corresponds to a positive value of x dot. Okay. In that case, what you have is this dx dot by dt. Okay, what do we have? You have dx by dt, that is the first equation. This is equal to x dot. So if x dot has a positive value, see this corresponds to, see you compare with this ax plus by, by is x dot. So b is equal to, which is positive. Okay. Therefore, what happens to the characteristic here? See that dx by dt is equal to x dot, means if you take a positive value of x dot, you see that x is increasing while crossing the positive x dot axis. And a similar statement when x dot, see, x is decreasing while crossing the negative x dot axis. And what does that mean? That means, see, it goes from, this is the first quadrant, this is the second quadrant, this is the third quadrant, this is the fourth quadrant. So the behavior that you have here is that x is increasing while crossing the positive x dot axis, means it moves from here to here. All characteristics on this side they all move in the opposite direction. So they cross either from the second quadrant to first quadrant or from the fourth quadrant to third quadrant. Okay. So second quadrant to first quadrant, or they cross from the third quadrant, fourth quadrant to third quadrant. That is another inference that we make. So all this we are just making inferences without solving the equation. I mean, this is what the theory of differential equation is all about. Without solving the equation, you keep reading the behavior of the solution. Okay, that is why you need a theory. These are very fairly elementary calculus that you are using in this and little bit of dynamics that you are using to make these inferences. Yeah, or from fourth quadrant okay. That is one inference that you are making. or a spiral it circles the origin in the clockwise so if you have a closed path, it will be always moving in this direction, and if you have a spiral, then it will be always moving in this direction, or something like this. It is closing in, then it will be always moving in this direction. Always the direction is going to be in the clockwise direction in this case. Okay. So there, of course, the values of q and k do not matter. Okay, because it is just using this information dx by dt is equal to x dot. Now the second inference that you make is that a characteristic x-axis always orthogonal. Why it is so? See, you have this again, this equation dx by dt equal to x dot. Now we are talking about crossing x-axis. Consider a point on the x-axis, something like 0. On the x-axis, you take a typical point 1, 0. That is the positive part. How does it cross there? You see that what you have is dx by dt equal to 0 at 1, 0. What does it mean? X is a constant when you trespass the point 1, 0. Okay, that happened, that is the x coordinate do not change, which means that along this axis it could be moving only in this direction. It can be like this, but over here the tangent to the curve will have to be just orthogonal. So everywhere on this line, this is the x dot, you see that dx by dt equal to 0, which in turn tells that x does not change while it crosses the x-axis. Okay, and that is the inference. So it crosses the x-axis. Always does it orthogonal. That's an inference that you have. Now we look at the various cases. We take the case where k square is greater than q. K square is greater than q means what are the roots of the characteristic polynomial? See, the characteristic equation is, see, the roots are lambda equal to minus k square root of k square minus q, corresponding to plus and minus, two roots are there. So if k square is greater than q, then you see that this is going to be We are talking about the positive square root of a number. So it is minus k plus square root of this, and you can easily see that what happens in magnitude, the magnitude of this is going to be less than the magnitude of this. Therefore, you see that both lambda 1 and lambda 2 are negative. If k square is greater than q, this is what you infer. Right. Now we take up the case A. In this, q is positive and is positive. So you see that actually lambda 1 into lambda 2 is going to be what? Lambda 1 into lambda 2 is going to be minus k plus root of k square minus q. Okay, lambda 1, lambda 2, from this equation itself you can write. What is the equation? The equation is lambda square plus 2k lambda plus q. So if you write this as lambda minus lambda 1 into lambda 2, then lambda 1 lambda 2 equal to q. Okay, and if q is positive, then lambda 1 lambda 2 is positive. Okay, then what you have is that either both lambda 1 and lambda 2 are positive, or both lambda 1 and lambda 2 are negative. But real and distinct. As long as q is positive, you see it's going to be distinct. They are also going to be distinct. Real, distinct, and having the same sign. This is the scenario. So this is so what is the nature of the equilibrium point? Is a nodal point. Then we can also say something more about this. What happens? Suppose you have lambda 1 positive, lambda 2 positive. Then you see the corresponding eigenvectors, where will you find them? See, they have to be along this direction, in the first quadrant or the third quadrant. So you see, so the corresponding rectilinear characteristics are these half lines. This half line, this half line, this half line, and this half line. So this one corresponding to lambda 1, this is also corresponding to lambda 1. They are positive. Okay, that's what I analyzed first. Okay, because these eigenvalues also give you the information about where the corresponding vectors are going to be, eigenvectors are going to be in this case. I mean, not in every case. So this is very much dependent on the fact that dx by dt equal to x dot. Because you see that there a equal to 0 and b equal to 1. That's the reason. Yeah. So since both lambda 1 and lambda 2 are positive, you see that the directions or the paths along this is going to be away towards these two directions. Okay. And then you can find out what the behavior of this. You see, you have you can see that one of them is that depends on the relative value of lambda 1 and lambda 2. So it could be something like this. That depends on the relative value. All characteristics are going to be like this. But that, as I warned you, it is not. It may be along lambda 1 or lambda 2 depending on the relative value of this. So the directions are from 0, 0, and the exact direction depends on the relative that you can easily write down. I leave it to you to write down what it is. Okay. Likewise, if the rectilinear characteristics are all in quadrant 2 and Q4. Then both are negative. Therefore, what happens is the situation is you get a stable equilibrium. One corresponding to lambda 1, the other one corresponding to and of course relative values would matter, and you can easily work out what the directions are. Again, this is a nodal point. Stable equilibrium. Now one can be more specific and say all characters non-linear tangent to the origin at the origin to the rectilinear characteristic whose slope has okay. Now you see that if you have this scenario, suppose this is lambda 1, suppose this is corresponding to lambda 1 and lambda 2, they are the slopes. Now you see whose absolute value is, what is the slope? So slope of lambda 1 is bigger than the slope of lambda 2, or lambda 1 is greater than, or mod lambda 1 is greater than mod lambda. Okay, so this is the scenario. And here, of course, what do you have? Mod lambda 2 is greater than mod lambda 1. Okay, so you can use this to find out along which direction the what is called non-rectilinear characteristics will enter the origin. So we take the case K is positive. If K is positive, then we have as I said, what you have is root of, okay, equal to minus K, K is positive, plus or minus root of K square. Then both lambda 1 and lambda 2 are negative. And the characteristics, rectilinear characteristics in Q4. Now, if K is negative, then you have unstable equilibrium. Because both lambda 1 and positive and rectilinear characteristics are Q3. This is just an application of the theory we have developed in this special case, which corresponds to a dynamical scenario. So it's really worth looking at. Okay. So if Q is negative, then you see that lambda 2 is negative. The lambda 1, lambda 2 corresponds to that. So you have what is called saddle point. The characteristics are one rectilinear, Q1 and the other Q4. Now we take up case 2. Let me just quickly run through this. Take the case K square equal to Q. In that case, real and equal. So we get a degenerate nodal point. So the rectilinear characteristics are or K positive, we get stable equilibrium. K negative, unstable. Now we take up the case 3. I'll just finish this and then leave you. Just a couple of minutes. If you wait, I think it will be over. Case 3. This is where K square is less than Q. One A, K equal to 0, then we get vortex point. See, your equation would become in that case d2x by this will lead to simple harmonic motion. For Q is greater than K square, so Q is positive, so you get simple harmonic motion, you get vortex point. Paths are characteristic ellipses. Now B, K greater than 0, then you get stable spiral point. K negative, then you get unstable. So these conditions would influence the direction. Now you see, if you have the case, what is K positive? When K positive, the situation is this. K is the, see, you have the damping force there. So the damping force is, this is what you have, d2x by dt square. This is the damping force. If K is positive, then what happens? You have the thing pulling back. So what happens is, you see the path in the x dot plane, what happens is that you will have spirals either like this, okay, all this will be like this. Okay, so the spirals will be just collapsing to the 0, 0. Now when K is negative, the scenario is, this is K positive, K is negative, what happens is that this force will, with velocity, you see, it is going to be the magnitude will be very strong. I mean, start increasing. So what happens is the amplitude will start, oscillating like this. It will just oscillate like this and go away. Okay. Right? So that is the situation that you have. So you get the whole thing will be unstable. So you have the corresponding spiral running away. So the amplitude will start increasing and will eventually go to infinity. That's the scenario that you have. And I think I'll stop here and then take up an interesting problem of, I'll just make some remarks later in my next lecture before I enter something like Lyapunov stability theory. Before that, I'll just say something about what is called the equilibrium points of a pendulum. Okay, thank you very much. Do you have any questions?